Hey everybody, this evening I'm going to talk to you about using integrated rate laws. So, to sort of recap and put this in context, initially when we talked about kinetics, we talked about average rates. And this let us write the rate of reaction in terms of any reactant or product in a particular reaction. Then we went on to talk about how rate changes with changes in concentration, or use the differential rate law for the reaction. But often we don't care necessarily about the rate per se. We care more about how concentration changes with time, and that's the purpose of these integrated rate laws that we're going to talk about today. Now, admittedly, we're going to simplify things. We're only going to talk about unimolecular reactions. These are reactions where we have a single reactant. Okay? In the textbook, you'll find this chart. It's table 13.1, and this is a summary of integrated and differential rate data and rate laws for the three most common orders of reactions: zero order, first order, and second order reactions. The first column obviously gives you the order. The second column gives you the rate law, or what is really the differential rate law. The third column gives you the units for the rate constant for that particular order. The fourth, fifth, and sixth columns are where we want to focus our attention right now, and that is on the integrated rate law, the graphical representation of that integrated rate law, and then the half-life equation also associated with that particular integrated rate law for that particular order. If you pay a particular attention to columns 4 and 5, for a zero order reaction, you will notice that a plot of concentration versus time yields a straight line. And the equation of that line is given as the integrated rate law in column 4. And you see a graph of concentration versus time there in column 5. And you'll note from that graph you can get two very important pieces of information. The y-intercept is the initial concentration of A. And the slope is equal to minus K. So if you know the slope, you can find the value of K. There's a similar approach for first and second order reactions as well. For first order reactions shown in the middle, we have natural log of A versus T that yields the straight line. And you notice the equation is written in two different forms there. The top one is the y equals mx plus b form, and probably the one you want to focus on. The bottom one is just a condensed version that really, for our purposes right now, doesn't help us a lot because not everybody's comfortable with the laws of logs. Okay, but a plot of natural log of A versus T gives us a straight line. Again, notice the negative slope. So the slope equals minus K here, okay? And the y-intercept equals the natural log of the initial concentration of A in this scenario. And then finally, the second order reaction, the plot of 1 over the concentration of A versus T is linear. You'll notice it is the only plot with a positive slope. And so the slope here is equal to K, and the y-intercept is equal to 1 over the initial concentration of A. The respective half-life equations for each type of integrated rate law are given in the final column there, column 6. Those are derived by figuring out the amount of time that it takes for the concentration of A at time t to be 1/2 of the original concentration at time 0. The textbook will give you the derivation of the equation if you're interested in that kind of thing. But more importantly here right now is what you want to know is which equation is associated with which order. And remember that these equations are going to be provided for you on an assessment. We want to know you can use the equation, not that you can memorize it. So let's look at an example then. So let's presume we have our reaction here of AB going to A plus B. It's decomposing. It's unimolecular. Okay, and let's say that we did some experimentation on this, and we found ultimately, after measuring the concentration over various periods of time, that a plot of the 1 over the concentration versus T gave us a straight line, or the straightest line. And the slope of that plot, 0.055 molarity to the minus 1, seconds to the minus 1. Armed with that information, let's try to answer 4 questions. What is the order? What is the value of the rate constant, including units? Let's write the differential and integrated rate laws. They're 2 separate laws for this particular reaction. And then, if the initial concentration of AB is 0.150 molar, what is that concentration after 155 seconds? Okay, so let's tackle these 4 questions in order. So the first one, what is the reaction order? Well, if you go back to the table shown at the beginning of the video, you're going to notice that a plot of 1 over AB versus time gives that, if that yields a straight line, that means the reaction is second order. For a second order reaction, you will also notice that the value of K is equal to the slope. Okay, and since the slope was 0.055 molarity to minus 1, seconds to the minus 1, that must be the value of the rate constant. Which brings us to question 3. Write the rate laws for the reaction. Now we have the differential rate law and we have the integrated rate law, so let's tackle those one at a time. The differential rate law. Rate equals 0.055 molarity to the minus 1, seconds to the minus 1, times the concentration of AB raised to the second power, because this is a second order reaction. The integrated rate law, 1 over the concentration of AB at time T, at some point in the reaction, is 0.055 molarity to the minus 1, seconds to the minus 1, times T, plus 1 over the initial concentration of AB, or AB at time 0. The final question is, if the initial concentration of AB is 0.15 molar, what will the concentration be after 155 seconds? This is looking at concentration over time, so we're going to use the integrated rate law that we just wrote, and we're going to plug in the data. So we get 1 over AB at time T, in this case, time will be at 155 seconds, equals 0.055 molarity to the minus 1, seconds to the minus 1, times 155 seconds, plus 1 over 0.0150 molar, or the initial concentration of AB. Returning to our trusty calculator, we calculate this out, and we get that the concentration of AB after 155 seconds will be 0.0658 molar. Hopefully this clears up a little bit of the confusion around integrated rate laws and over the concentration versus time data. And I look forward to chatting with you all again real soon in future videos.